Brettell, also from Victoria University of Wellington, and next going to be talking about characterizing matroids representable over all fields of size at least 4. Continuation talk. Thanks, Nick.
Thank you. So my title is less pithy than Jeff's, but as you've said, it is a follow-on talk. So for my starting point, I'm going to think about regular matroids. So of course, a regular matroid is one that's representable over every field. And we know there are these 3 different ways of characterizing a regular matroid. Jeff has talked about the excluded minors. I'm going to focus on these other 2 approaches. So first of all, what I'm calling here an algebraic characterization. We can say that a matroid is regular if and only if it has a representation by a totally unimodular matrix, by which we mean all of our square submatrices have determinants that are either -1, +1, or 0. So this is one nice characterization. Another characterization, we could look at finding a finite set of fields such that you're representable over this infinite set of fields, if and only if you're representable over this finite set of fields. For regular matroids, GF2 and GF3 works. You can in fact do GF2 in any field that has characteristic not 2. So that's the picture for regular matroids. If we move to near regular matroids, so ones that are representable over every field of size at least 3, again we have 3 characterizations of this type. So first of all, for what I'm calling my algebraic characterization, now we're looking at representations over the rationals but extended by some indeterminate alpha, and we're going to require that our square submatrices, the non-zero subdeterminants, are positive or negative powers, positive or negative product of powers of alpha and 1 minus alpha. And for our finite set of fields characterization, we know that we're representable over all fields of size at least 3, if and only if we're GF3, GF4, and GF5 representable. And thanks to Rhiannon, Dylan, and Stefan, there's also an excluded minor characterization written up as well. So moving on to the focus of this talk, matroids representable over all fields of size at least 4. The question I'm interested in is finding characterizations of these 3 types for this class. And the short answer is that we don't have any such characterization as yet. This is not going to be a talk where I'm giving new characterizations, but instead giving a bit of a status update, talking about what we know towards finding, hopefully, some characterizations of this type, or at least of focusing on the first 2 types here. Okay, so what do we know? So Jeff's talk mostly sidestepped the issue of talking about partial fields. I'm going to face them more head-on. So if you haven't seen a partial field, the notion of a partial field before, what you can do is think about them as being a structure that we use in order to capture this notion of an algebraic characterization. So what I'm going to do is consider a pair RG, where R is a commutative ring. So this is our algebraic structure that we're working over. And for the G, this is going to tell us what we're allowed for our determinants of our square submatrices and our representations. So to be P representable for some partial field P, this is like representability in the sense that the normal sense that hopefully you're all used to, except that we also are going to require that our subdeterminants for our square submatrices are in this group G when they're non-zero. So reframing things in this way, we can now talk about regular matroids as being representable over this partial field where we're working over the rationals and we're saying that our subdeterminants are in either -1 or 1 when they're non-zero. For near regular matroids, the partial field now of interest is this one I've called U1 here, with the rationals extended by alpha, and our subdeterminants are members of this group with generators -1 alpha, alpha -1. Okay, so we want, so now our algebraic characterization is, in other words, trying to find a partial field P such that we're in M4 if and only if we're P representable. Okay, so that brings us to K-regular matroids, which you'll know about now thanks to Jeff's talk. I wanted to focus on a few aspects of this. So one way you can think about the K-regular partial field is that it's the most general partial field that your rank 2 uniform matroid is representable over. So more specifically, for UK, the K-regular partial field, most general partial field that U2, K plus 3, is representable over. And so a way you can think about this, here I've got some representations of rank 2 uniform matroids up the top here, where our alpha or alpha and beta are representing some element that's not 0 and not 1. And if you look at the subdeterminants, if you treat alpha or alpha and beta as an indeterminate here and look at the subdeterminants, then you get these groups that correspond to our 1 regular or 2 regular partial field. Okay, so so this notion of a universal partial field, it's treated much more rigorously by Rudy and Stefan, but I'm just here in this talk going to think of it as the most general partial field that a matroid is representable over. Okay, so as we know, U36 gives us an example of a matroid that's in M4 but is not 2 regular. So 2 regular isn't, or this 2 regular partial field is not the partial field we're looking for. So I'll come back to that in a moment. First, back to this, back to 2 regular matroids. We did go through the trouble, as Jeff mentioned, of coming up with a excluded minor characterization for this class. And from one point of view, there are 2 aspects to it. One was bounding the size of your excluded minor. We found that it had most 15 elements. And then on the other side, coming up with a computer search to find all of those excluded minors up to 15 elements. So this latter part was a project I did with Rudy when I had a postdoc in Eindhoven 5 or so years ago. Then we find that these 4 matroids in green turn out to be in our class M4. So we have a picture that looks like this to begin with. So our 2 regular matroids are a proper subclass of M4, and these are the excluded minors that are in that class M4. So towards finding this partial field that is going to characterize our class M4, what we can do is look at the universal partial field of these 4 excluded minors here. And so it turns out for 3 of the 4, the partial field is what's known as the 2 cyclotomic partial field, or this one denoted here, K2. We're again looking at rationals extended by some alpha, but we're allowing subdeterminants that are products of powers of alpha minus 1 alpha, and now also alpha plus 1. And just as a bit of an aside, one nice interesting result of Rudy and Stefan's about these K2 representable matroids, we can also think of them as matroids that are GF4 representable and have at least two inequivalent GF5 representations. But back on task, Rudy and Stefan also found that there was this matroid that is not K2 representable and is in M4. This 9-element matroid, I'm calling it A9 here just because it looks a bit like an arrow and has 9 elements. And so we can play the same game and look at what is the universal partial field of this matroid. And we get this P4 partial field where what's changed from K2 is we've now got this alpha minus 2 appearing here. So we can also have factors of alpha minus 2 or powers of alpha minus 2 appearing as in our subdeterminants. So that was the sort of state of play of this back in 2010, I guess. So having done this work to be able to compute these excluded minors for two regular matroids, it was little effort to do the same thing but with these partial fields K2 and P4. So using essentially the same code but rejigged these different partial fields, had a go at finding the excluded minors up to a certain size for these partial fields. So first of all for K2, and the numbers of excluded minors here I'm not really interested in, but I have shown them. So on the right you can see the number of each size. But what I'm interested in is there are these 6 up to duality in this operation delta y that I'm not going to get into. There's 6 that are in our class M4, and in particular 2 that are not even in P4, not even P4 representable. So this tells us P4 is also not the partial field we're looking for to characterize M4. So then we can repeat this with P4, find the excluded minors for the class of P4 representable matroids. We find a further matroid that is in M4. So we now have these 3 matroids that are excluded minors for P4, but are in my class of matroids representable over all fields of size at least 4. And so these 3, we can look at their universal partial field. It turns out that they all have a slightly different one, but the most general of those 3 is this that I've given here. So we've now got another generator appearing for our group. I've got 2 alpha minus 3 has popped up there as well. So for P4, it was kind of a, I would say, compelling conjecture as to a partial field to characterize representability over all fields of size at least 4. You need to be able to map this alpha to something that you can add 1 to, or subtract 1 to, or subtract 2 to, and get something that's non-zero. This one's less compelling. Once you've got 2 alpha minus 3 appearing in there, you might ask, well, why not some other generators as well? Why not a 3 alpha minus 2 or something, perhaps? And so I don't have a good answer to that, only that we know of a matroid that requires this, but I don't know of any matroid that requires any of these other generators that you might be able to come up with. So anyway, putting that into pictorial form, our green ellipse here is K2 representable matroids. A9 was this matroid that Rudy and Stefan found that was not K2 representable, but in M4. There's a bunch of other ones, including a couple of matroids that are not even P4 representable, but all of the matroids that we know of, so this is of up to size at least, up to size 14, that are in our class M4 are all representable over this partial field here that I'm calling O. Okay, so my conjecture for now is that this is the partial field that characterizes representability over all fields of size at least 4. Yeah, question? 14's just what the computer search has been able to get up to. So yeah, we made it as efficient as we could, and that sort of was where we got to. If you put in more work, you could perhaps get another element or 2 or so, but at a certain point your computer's not going to be able to help so much. But yeah, 14's just what we could get up to with some effort, but not too much effort. No, we don't have any bound on the size of an excluded minor, even a ridiculous bound for these other classes. Okay, so that's sort of the first half of my talk. So if you've tuned out, feel free to tune back in again, because I'm going to talk about this other sort of characterization, this second one I mentioned, finding a finite set of fields, finite set F, such that if you're representable over each field in F, then you're a member of this class M4. So the first thing that you can observe is that there is such a finite set of fields. So I'm going to use well-quasi ordering for GF4 representable matroids to show this. So if you take all of your excluded minors for M4, put them in this set I'm calling here E4. All of the excluded minors for M4 that are GF4 representable. And then since they're excluded minors for M4, there's some larger field that they're not representable over. So I'll call this Q sub n, and so I get a set of all of these smallest larger than 4 size fields that they're not representable over. And then if I tell you that I've got a matroid that's GF4 representable and representable over each of those size fields, then it can't have any of these excluded minors as a minor, so it's in our class M4. Okay, so the well-quasi ordering thing was just in order to make sure that my set here is finite. My E4 is going to be a finite set. Okay, yep. To show you that there is a partial field for an infinite. There certainly is if you're dealing with a finite number of fields. If you've got an infinite number of fields, I'm not sure. Yeah. Okay, so one observation at this point that, as part of why I mentioned this observation and gave this proof here, is that this open problem 2 is an easier problem than the excluded minor problem, in the sense that if you know the excluded minors, then this is just a triviality. It just falls over from that. Okay, so my hope is even if we can't find all of the excluded minors for our class M4, perhaps we can still find a finite set of field characterization nonetheless. Okay, so the other side of that, we know from these computer searches all of the excluded minors up to size at least 14. So we can ask, well, what seems like a candidate set of fields for our finite set here? For each of them, let's look at the field larger than 4 that they're not representable over. And it turns out that all that we get is GF5 and GF7. Okay, so for these excluded minors that we know, up to size 14, all of the GF4 representable ones are either not GF5 representable or not GF7 representable. So optimistically, you could ask, well, is it enough to say if you're GF4, GF5, GF7 representable, then you're also in this class M4. And so that brings me to some recent work with Rutger, where I'll get to what we were able to show in a moment. But first, I want to introduce another partial field, one from Rudy and Stefan's work again, the Gersonides partial field. And so this is a partial field where we're talking about matrices are those that are representable over the rationals, and all of your subdeterminants are products of powers, positive or negative products of powers of 2 and 3. Okay, so for those familiar with dyadic, it's similar to that, a similar structure to that. We've also got 3 as a generator here in the group. Okay, and so a matroid that's representable over this partial field, if a matroid is representable over this partial field if and only if you're representable over every field with characteristic not 2 and not 3. So in particular, you'll be GF5 and you'll be GF7 representable. So we sort of started asking the question, if you're GF4 representable and you're representable over this partial field, is that enough to guarantee that you're in this class M4? And we don't have a conclusive answer to that question, but we can say something. And so what we can say, again, needs me to introduce yet another partial field. So this partial field, this time we're going to be working over a quotient ring. So I'll take the rationals So polynomials in alpha, and then I'll mod out by this 2 alpha minus 1 times alpha squared minus alpha minus 1. Okay, so this is the ring that I'm working over, and then my subdeterminants are going to need to be these powers of alpha minus 1, alpha, alpha plus 1. Okay, and so what we're able to show is that this partial field characterizes being both GF4 and Gersonides representable over GF4 and this GE partial field. Okay, so just a couple things to note about this partial field. So if you look at a matroid that's representable over this partial field and you ask if it's representable over some other finite field, you're going to need to have something that you can map this alpha to, such that either you've got 2 alpha minus 1 is 0, or you've got alpha squared minus alpha minus 1 is 0. Okay, so something behaving a bit like a half, or something behaving a bit like a golden ratio here. So yeah, how did we prove this? It's yet another application of the lift theorem due to Rudy and Stefan. So pretty much all of the results of this type, where you say something like matroid's representable over, the matroid's near regular if you're GF3, GF4, GF5 representable, that can be seen as an application of this lift theorem. What I wanted to say about this is that it really seemed like this lift theorem had been mined for all it was worth, in the sense that haven't been able to get it to work for anything you could think of since the stuff that Rudy and Stefan did, but this is one further example where it actually works, so that was quite nice. Okay, so what does it tell us back to our original problem? So you can look at if you're B representable, you can ask if, in partial field terminology, if there's a partial field homomorphism to other finite fields. And so a B representable matroid is certainly representable over all fields of size at least 4, except those of the form GF2 to the k or GF3 to the k, where k is odd. Okay, and in fact, if we focus on GF8, which is one example of that, there is no partial field homomorphism from this partial field B to GF8. So it gives us the possibility that a matroid could be representable over this partial field, but is not GF8 representable. However, we can't conclusively say that there aren't that all of the B representable matroids don't actually turn out to be in M4 until we know of a matroid that has this as its universal partial field, which we don't have as yet. So we're on the lookout for a matroid with this as its universal partial field, and then we could say that that GF4, GF5, GF7 is not enough. You'd also need GF8. But from our computations, we know that such a matroid would need to have more than 14 elements. So coming up with such a matroid is not such an easy thing. Okay, so let me finish just by saying I've got a conjecture here that I didn't get a proper chance to okay with Rutger, but I'm going with that your matroid is in this class M4 if and only if you're representable over GF4, GF5, GF7, GF8, being 2 cubed, but also GF27, which is 3 cubed. Yeah, so I'll finish there. Thanks.
Is there a question for Nick?
Could you go back to the slide where you introduced B? Or no, this slide, okay. So you say you don't know of any matroid that is representable over B, but not over GF8. But you can still apply the lift theorem to the partial field product of B and GF8, right? and then you would get a partial field that has a map to GF8.
So I'm just saying that we don't know that there are any matroids that require to be representable over this partial field.
Yeah. But if you're sort of making an outer approximation of the class, right?
Yeah.
By refining the partial field. And
Yeah.
saying you even if you're not sure that you may already have the representability of GF8, but you can ensure it by applying the lift theorem to the product.
Right, so you're going to do a lift with GF8 with
Yeah.
this partial
Yeah.
field. Yeah.
And then you rinse and repeat.
Right, yeah.
And for your conjecture on the last slide,
Yeah.
you could take a lift of the partial field product of those finite fields, right? What does that look like? And does it perhaps already have a homomorphism to?
Usually, we did look at a few different things like that, and usually the numbers, the quantity of the fundamentals didn't work out for us to be able to apply the lift theorem in any of those cases, which was kind of why we were a bit surprised that this one worked for B. It seemed like, so I'm not sure that that doing a lift for the 4, 5, 7, 8, 27 would get you anything, because I think we did try something like that, and it.
So you have a computational problem with it, or it just doesn't give anything interesting?
It just, didn't seem to give us any. I can't recall exactly.
Okay. Thanks.
Jim.
It's not something that we've tried. I mean, I guess it is closely related to the general problem of being able to, or trying to come up with a matroid that has some partial field as a universal partial field. Yeah. True. Yeah, and I do think an approach like that is something that we should try but haven't yet. Yeah.
Okay, let's thank Nick again.